Good morning, students. Welcome to Real Analysis lectures. In this lecture, we'll discuss about countable sets. Okay. So to start with, we'll define what is meant by equivalent sets. So two sets A and B are said to be equivalent, which we denote by now onwards with this symbol, if there exists a one-to-one correspondence. Okay. That means for every element of A here, there is an element associated to B. Similarly, for every element of B, there is an element associated to from A. Okay, so there is, if at all there is a one-to-one correspondence, or mathematically, if we say that if there exists a bijective map, then those two sets we will call it as equivalent sets. Okay, fine. You can take it as a small exercise, show that this relation is actually an equivalence relation. What is meant by an equivalence relation? It is reflexive, which is obvious, and symmetric. That means whenever A is equivalent to B, then we want to show that B is equivalent to A, and transitive. Okay, so what is meant by transitive? That if A is equivalent to B and B is equivalent to C, then we want to show that A is equivalent to C. These three follows immediately. You have to just write it. Okay, fine. Now with this notion of equivalent sets, we define what is meant by a finite set, infinite set, countable and uncountable set. Right. So a set is said to be finite if it is an empty set or it is equivalent to 1, 2, 3 for some n. Okay, so whenever we say that a set is finite, it should be an empty set or it should be equivalent to, there should be a correspondence from a to this set 1 2 3 n for some n. Okay, and when we say that it is an infinite, if that there does not exist any n, that means if a set is not equivalent to any finite set, okay, then you can call it that set as infinite set. Right, now a set is said to be countable if either that set is finite or it is equivalent to n. Okay, that means a set A x is infinite. If at all it is infinite, then it should be equivalent to n. So if it is finite, then we will call it as countable. If it is infinite, then it should be equivalent to n, then we say it is a countable set. Right, fine. So any set having correspondence with n, one-to-one correspondence, we call it as countable set. Right, what are the obvious examples? The first one is n is countable because n is equivalent to n itself, and z is also countable. Okay, so if you see z, what we have here is, okay, you can, how we will relate that to n, we'll try to understand. So negative integers are there and positive integers are there. Right, so somehow we have to map these negative integers to some natural numbers and positive integers to some natural numbers. Obviously the one way we can do is we can map all these positive integers, okay, means are n greater than or equal to 1, to even. Okay, because you can split your n into even and odd numbers. So all this we will map it to even accordingly. Okay, and all this even in negative integers we will map to odd natural numbers. Okay, and obviously how we can do it? So if this is the function, if n is less than, if n is greater than or equal to 1, then you send it to 2n. Okay, that means 1 is going to 2 and 2 is going to 4, 4 is going to 8 and so on. Right, and if n is less than or equal to 0, we are sending to odd number in the form of 1 minus 2n. Okay, you can check that if n is less than or equal to 0, then 1 minus 2n is greater than or equal to 0, so therefore it is a natural number. Right, okay, but this is the main idea. We will send to all negative integers to odd natural numbers and this positive integers to even numbers. Right, and showing everything is 1 1 and 2, all these things is routine. You can check this one. Okay, I skip that one. Fine. Not only n, we'll show that this, because many times showing every set is equivalent n is not possible. Instead, what we'll show is first that n cross n is countable, and then we use this to show some other type of sets are countable, right? So how we will show that n cross n is countable, that means how we will show that there is a bijection from n to, how we can get a map from n to n cross n. Okay, see, think there are many ways you can do it. Of course, you take any natural number. For example, of course, it is either it is even or odd. If it is even, there is no odd part. Okay, if it is odd, see, suppose for just let me call it, suppose 18 you take. Okay, then you, because it is even number, you take out the maximum even available, that means maximum power of 2. So I can write this as 2 into 9, right? Suppose if I take 15, there is, it is odd number, so this I can write as 2 power 0 into 15, right? So what I am trying to say it here is, any natural number you can represent in the form of something like, if you call it k is a natural number, you can represent this in 2 power some power of 2 power m minus 1 times an odd number, which is, you can call it as 2n minus 1, right? Here how you can write this you can write as 2 power 2 minus 1 into 9, you can write as 2 times 5 minus, that means 10 minus 1. Okay, this you, how you can write as 2 power 1 minus 1 into, of course, 2 times 8 minus 1. Okay, so you can see that this every number can be written in this form. So therefore this m and n, for every k there exist m and n, right? So you are getting a map here. So send f of k as m comma n, where this k can be written in this form. That means, for example, in this, how you get a 18, we are sending to what? We are sending to 2 comma 5, and whereas for 15 we are sending to 1 comma 8, like this, right? So with this correspondence, you can see that this n cross n and n have a bijection, therefore n cross n is countable, right? I hope this is clear, and all complete details are here. That is routine work, you can check it, and I have provided the clear one-to-one information, right? Now using this n cross n is countable, we can prove more general that if a and b, if a and b are countable, then a cross b is also countable. How we can prove this? That means, if at all, if now we no need to show that a cross b is having bijection with n. Instead, if we can show that this a cross b is equivalent to n cross n, that is more than sufficient, right? And that we can do it easily, because a is countable, so you have a map from a to n, and you have another map from b to n. So therefore their Cartesian f cross g, you can call it, that you call it as h. So h from a cross b to n cross n, obviously sending to f of a and g of b, will give a map from a cross b to n cross n, and remaining that map is bijection and all, you can see it from here, right? Fine. So if a and b are countable, then a cross b Cartesian product is also countable. Another interesting result about countable sets is that the countable union of countable sets is countable. That means, if ans are countable, then union of an, countable union, is also countable, right? How we'll prove that? Here we'll try to write this union of an as some proper way, so that we'll see whether we have any connection between a to n or n cross n. Okay, because each ans are countable, we can represent them in this notation, because it is a sum of equivalent to n. So a11, a12, a13, you can index them. Similarly, a2, you try to index a21, a22, a23. So this 2 represents set 2, and similarly an is an1, an2, an3, and so on. Now union of this ans is nothing but union of all such elements. So therefore union of ans is nothing but collection of all these elements of the form eij, where I is a natural number as well as j is a natural number. So therefore this pair belongs to n cross n, right? So we have got now this union of ans of the form aij, where this each pair I comma j is in n cross n, right? So that gives an idea to define a map from union of an to n cross n. Simply take any element this aij and define this as simply this suffix index I comma j. For example, a this element a11, a11 we were sending to what? The element 1 comma 1. If I take suppose a34, this we are sending to 3 comma 4, right? So in this way you can correspond each elements from this collection to n cross n, and we know n cross n is countable, so therefore this union of an is also countable. Of course, what we have shown here is the routine process of checking this 1 1 and on 2. Okay. Next is q. We all know that q is countable. Now we can give the proof using this notation whatever we have seen. So we want to show that this set of rational numbers q is countable. So the idea is the following: we'll try to write q is equal to union of some countable sets, okay? And by using the above result, because countable union of countable sets is countable, so we will idea is we'll try to represent q as union of some countable union of ans, where each an is countable. Then by previous result follows that q is countable, right? Now how is the idea is q is rational numbers, right? So what we do is we try to define this an is with fixed denominator, okay? So what is our an is m by n, where m is any integer. So m can be any integer, but we are collecting all rationals with common denominator. For example, what is a2 here? A2 represents all elements whose denominator is 2. For example, 5 by 2, okay, 7 by 2, 1 by 2, minus 3 by 2, all these such things, right? So we are collecting all such elements as in one set, namely a2. For example, if I call it as a10, so a10 represents whose denominator is 10, okay, like this. So if you collect all these things, we should by first at least sense that by collecting all such things our q will be complete. So q is equal to union of an, first we want to show. So we have defined our an as by having the common denominator. Then we'll show that q is equal to union of ans. It is not at all difficult to show, and we'll show that each an is countable, right? Why? Obviously each this is a subset of q, okay? So union of ans is subset of q. Now we want to show that q is contained in every element of q is contained in one of these ans, right? That is clear, because if you take any m by q is of the form m by n, then you can write it in such a way that denominator we can make it as a natural number, okay? For example, what I mean to say is this you can write as 3 by minus 3 by 2, okay? So 3 by, instead of writing 3 by minus 2, you can write this as minus 3 by 2, right? Okay. So therefore this actually belongs to a2, right? That means every rational number actually belongs to an for some n. Therefore q is equal to union of an, right? So it is enough to show that each an is countable. But that is clear, because what is this an? How you can correspond an? Obviously, if you take this an and z, they are having correspondence, because in this a and n is fixed, okay? So what is varying is only m. For every integer m you have here, so simply you can send it m by n to m, that is the function, and show that it is 1 1 and on 2, okay? So what is main important thing you should understand is how we are getting map. That is important. Not after defining the map, whatever you are showing is simply based on calculation. Show that it is 1 1. So show let f of x is equal to f of y. Then show that x is equal to y, right? And show that it is on 2 and so on. But what is most important is how we are able to get this function. What is the idea to define such function is important, because an and z, they are very closely related, because in an, even though n is there, but n is fixed for each set an. If I say a5, the moment I say a5, then every element in that a5 denominator is 5 only. So whatever is there, you only worry about or concentrate about numerator, right? So you can see that an and z are having one-to-one correspondence. So therefore, as z is countable, an is countable. So as each an is countable, q is countable union. Therefore, q you will get as countable union of countable set. So therefore, q is countable, right? Fine. Now the other interesting result which we will see is that uh, you take any subset of n, then it is countable. So any subset of n is countable. Obviously, if it is a finite set, then it is already countable. So what we have to prove remaining is that if it is an infinite subset, even if it is an infinite subset, we will show that it is still countable. Okay. So how we do this here is start with an infinite subset of n, because as it is a non-empty subset, by well-ordering principle, what we know is that what well-ordering principle says that every non-empty subset of n has a least element. So say call it x1 is least element of a. Okay, that means every element of a is bigger than or equal to x1, and of course they are all subsets of n. So what we can do is x1 is obviously bigger than or equal to 1, right? So x1 is the least element of a. Now how we get the next one is, from this a you remove this set element x1. Again, because a is non-empty, this is still non-empty subset. Okay, again apply well ordering principle. For this set you have a least element, call it x2. Of course x2 is definitely not equal to x1. So therefore what you get is, and x1 is least element of entire every element of a. So what we get here is x1 is strictly less than x2, right? But x1 is bigger than or equal to, x1 is either 1 or bigger than 1. That shows that x2 is bigger than or equal to 2, right? Either it may be 2 or bigger than 2. It cannot be 1, right? And so on. So what you have observed is, if we repeat this, keep on doing, you get a sequence x1, x2, x3 and so on, where xn is bigger than or equal to n, and it is the least element of the set a minus, by removing the previous n minus 1 elements. Okay, what we show is that this a and x1, x2, xn, if you keep on taking, there is no left element left out from this after removing. That means it is an empty collection we want to show, right? We prove this by contradiction. Suppose that this is non-empty collection. That means there exists an m in a such that m is not in this one. That means what? M is not equal to xi for every I. Okay, so therefore either m has to be greater than xi or m has to be less than xi, right? We'll collect this set as all index such that, so your s is nothing but you take an index if this xk is greater than this given m. Okay, right? Clearly you can see that by this observation, whatever we have observed here, xm is bigger than or equal to m. But by again from here, because of this one, m is not at all equal to any xi. So in particular m is also not equal to xm. That means xm is strictly bigger than m. So therefore xm is strictly bigger than m. This shows that this m, which is index, is actually belongs to s. This implies our s is non-empty collection. So therefore our s is a non-empty subset of n. So we can again apply well ordering principle, right? So that means by well ordering principle of s, Now by well ordering principle, this S has least element, call it as N. So N is the least element of S means what? If you see this, anything smaller than N is not in S. So 1, 2 up to N minus 1 is not in S, okay, and N is there in S, right? But what is meant by saying that 1, 2, what is meant by saying that this 1, 2, 3 up to N minus 1 are not in S? When they are not in S, if their value is less than M. Therefore, x1, we know x1 is less than x2, that we already have it, right? So each xn minus 1, each one is less than M. If at all they are greater than M, they are in S. Because they are not in S, so therefore their value should be less than M, right? Okay, fine. And N is in S, that means what? Xn is bigger than M. So if you combine these two, what we get here is that therefore M xn minus 1 is less than M and M is less than xn. Okay, so we should get somewhere contradiction to this. And how we get that contradiction is because this xn, the way we have selected xn, is the least element of A by removing these elements, right? So other than this x1, x2, xn minus 1, whatever elements are there in A, this xn is the least element of that, right? So therefore xn should be less than or equal to any element of A not coming from here. In particular, M is from A, so therefore we get that xn is less than or equal to M. So this is a contradiction to xn is less than or equal to M and xn is greater than M, right? So these two are contradicting to each other. Therefore what we are having is that contradiction is arrived because we have assumed that this is a non-empty collection. Therefore, this has to be empty collection. So therefore, A is actually x1, x2, and so on. That means A is countable set, right? So what we have proved is that any infinite subset of N is countable. As a corollary, you can easily observe that if you take any subset of a countable set is countable. Okay, fine. Just one last one we'll discuss, which says that many times you all might be knowing the open interval 0 comma 1 is uncountable. Okay, so we'll try to show that this open interval 0 comma 1 is uncountable. Of course you can, same thing you can do it for closed interval also and so on. So we prove again by contradiction. Suppose assume that 0 comma 1 is countable, so you can represent them in the this notation. So you call it x1, x2, xn. And because they are elements between 0 and 1, you can represent them in the decimal form of this following: a11, a12, a13, and so on. Okay, similarly how we will represent x2: 0.821, a22, a23, and so on. Okay, and from this x1, x2, x3, what we'll do is, the idea is simple. We'll try to get an element which belongs to here but which is not equal to any one of this one. That will be a contradiction, right? So how we define a y, we'll take this diagonal elements. Using these diagonal elements, we'll define another element y, which is 0 point, okay, you call it like b11, b22, b33, based on diagonal elements. Okay, and how we do is, see, we want an element which is different from x1. Suppose you call it this is 0 point, say suppose my x1 is something like 0.53 and so on. Okay, so I want y, it should be different from this. Okay, so therefore x1 and y should be different. It is enough if it is different at this one place. So I will define my b11 which is different from a11. Similarly, y is different from x2 I want. So x2, suppose I will call it as 0.25 or 267 and so on. So y is different from x2. It is enough if it is different at second digit, this place, decimal place. Okay. So the idea is, you call it this bnn is, suppose if my ann, okay, is not equal to 2, then I will define my bn as, for example, here x1 is, because it is not equal to 5, so my y is 0.2 will come. and whenever my ANN is 2, at that time I will define this is another one, other anything different from 2. Say for example, I can define 3, I can define 5, I can define anything other than 2. So suppose example, I'll call it 3. Is this clear? So we are trying to construct an element which is not equal to any one of these elements. And how we are doing it? We are trying to at least make sure that this y is different from each xi at least at one digit, and that digit we are considering in the form of like diagonal places. Okay, fine. Now you can see that this y, okay, because it is 0 point something, this belongs to 0 comma 1, but y is not equal to any one of these xi's. Okay, because this y it differs with x1 at first position, and y differs at with x2 at second position, y differs with x3 at third position, and so on. So therefore y is not equal to xn for any n, right? Which is a contradiction, because we said that 0 comma 1 can be represented in x1 x2 xn ways, but y is an element which is not equal to any one of them. That contradiction arised because we have assumed that it is countable, right? So hence it cannot be a countable set. So therefore 0 comma 1 is an uncountable set, right? As a quick corollary, you can clearly prove that this r is uncountable. Why r is uncountable? Because 0 comma 1 is subset of r. If at all r is countable, then by using this corollary, every subset of a countable set should be countable. So 0 comma 1 has to be countable, but that is not true, because we know just now proved it is uncountable. So therefore r has to be uncountable set. Now so what are all we have seen is that q is countable, okay, r is uncountable. What about r minus q? So you can check that r minus q is also uncountable. Why? If at all r minus q is countable, if at all it is countable, then we know that countable union of countable sets is countable. So therefore r you get as a countable set, which is not true. Hence r minus q has to be uncountable set, right? These are the some of the results about countable uncountable sets. Okay, so next class we'll see about sequences, right?